A position reference system, or PRS, is the sensory backbone of any dynamic positioning system. Think of it as the vessel's eyes and ears in the vast ocean. This system constantly measures the vessel's exact geographical position, its heading, and any slight movements. It then feeds this critical information to the DP computer. The DP computer processes these inputs and calculates the precise amount of thrust needed from the propellers and thrusters to counteract the forces of wind, waves, and current. Without a reliable PRS, the DP system would be blind, unable to make the necessary adjustments to hold the vessel steady. It is the fundamental link between knowing where you are and staying exactly where you need to be. The importance of a stable and accurate PRS cannot be overstated, especially during critical offshore operations. When a vessel is engaged in tasks like transferring cargo to a fixed platform, every meter and even every centimeter matters. A sudden uncommanded movement could lead to a collision, causing significant damage or endangering personnel. Similarly, during diving support operations, the vessel must maintain its position with extreme precision. The safety of the divers below, connected to the vessel by their umbilical cords, depends entirely on the vessel's ability to remain perfectly stationary. The PRS provides this unwavering stability, creating a safe and controlled environment for these high-stakes activities to proceed without incident. Imagine the DP system as the brain and the thrusters as the muscles of the vessel. The PRS in this analogy is the central nervous system. It continuously sends signals to the brain, reporting on the vessel's state relative to its intended position. Even the slightest deviation is detected and reported in real time. This constant flow of data allows the DP system to orchestrate a seamless response, commanding the thrusters to push or pull with just the right force. This creates a state of equilibrium, where the vessel appears to be motionless, even amidst challenging environmental conditions. This stability is what defines dynamic positioning and makes complex offshore work possible and safe. The core function of the PRS is to provide uninterrupted, high-quality position data. The accuracy required can vary depending on the operation, but consistency is always key. For the dynamic positioning officer, understanding how each PRS works is fundamental. It is not just a piece of equipment, it is a vital tool that requires constant attention and verification. The DPO must trust the information being provided by the PRS, as the entire DP system's performance hinges on its reliability. A healthy PRS ensures that the vessel holds its ground, protecting the asset, the environment, and most importantly, the lives of everyone on board and in the water. To achieve robust positioning, DP vessels use a variety of PRS technologies, each with its own strengths and weaknesses. The most common is the Differential Global Positioning System, or DGPS. This system improves upon standard GPS by using a fixed, known ground station to broadcast corrections, significantly increasing accuracy. For even higher precision, some operations use real-time kinematic GPS, which can provide centimeter-level accuracy. For surface-based references, systems like FanBeam and Radius are popular. FanBeam uses a laser to track a reflective target on a nearby platform or vessel, while Radius uses a radar-like signal, making it more resilient in fog or rain where a laser might struggle. Another category of PRS operates independently of satellites or surface structures. Hydroacoustic systems are a prime example, using underwater transponders placed on the seabed. The vessel sends out an acoustic signal, or what we call a ping, and measures the time it takes to receive the reply from the transponders. By triangulating these signals, the system calculates the vessel's position relative to the seabed. Taut wire systems are more mechanical. They involve lowering a depressor weight to the seabed on a wire. Sensors on the vessel measure the angle of the wire to determine the vessel's movement from the spot directly above the weight. These systems are often used as backups due to their physical limitations. A less common but highly effective long-range system is Artemis. This technology uses a microwave link between two stations, one on the vessel and one on a fixed platform. It measures both the range and bearing between the two stations with a high degree of accuracy and is not affected by GPS signal disruptions. The variety of available systems is crucial because no single PRS is perfect in all conditions. DGPS can be affected by solar flares or signal obstruction, lasers can be blocked by fog, and hydroacoustic systems can suffer from underwater noise interference. A competent DPO must be familiar with the operational principles and limitations of each system installed on their vessel. Understanding this diverse toolkit allows the DPO to select the most suitable combination of PRS for the specific job and environmental conditions. For instance, in a busy field with many other vessels, a hydroacoustic system might face interference from other acoustic signals. In this case, a combination of DGPS and a laser-based system like fan beam might be a more reliable choice. The goal is always to have multiple independent sources of position information feeding into the DP system. This multi-layered approach ensures that if one system becomes unreliable, others are available to maintain a stable and accurate position reference for the vessel. For a vessel to be classified as DP2, it must be designed with redundancy in mind. This principle dictates that no single failure should result in a loss of position. This applies directly and critically to position reference systems. A DP2 vessel is required to have at least 3 separate PRS units online simultaneously during operations. More importantly, these systems should be based on at least 2 different technologies. For example, a vessel might use 2 DGPS units and 1 hydroacoustic system. This ensures that a single type of systemic failure, like a widespread GPS outage, will not disable all the positioning inputs at once, which is the essence of independence. The principle of independence is just as important as redundancy. Having 3 DGPS units from the same manufacturer is redundant, but they are not fully independent. They all rely on the same satellite constellation and could be affected by the same signal disruptions or software bugs. The DP2 philosophy demands independence in both principle and physical separation. This means using different technologies such as satellite, acoustic, or laser, and ensuring their hardware components like power supplies and cabling are routed separately. If one system fails due to a power loss in one part of the vessel, the independent systems connected to a different power source will remain operational, preventing a total loss of positioning capability. The DPO's role is central to managing this complex arrangement. Before any operation begins, the DPO must perform rigorous checks on each PRS. This includes verifying calibration data, ensuring each system has a clear signal, and confirming that it is being correctly recognized by the DP system. The DPO sets up the DP console to actively use the selected systems, carefully monitoring their performance throughout the operation. This involves watching for any signs of instability, such as fluctuating position data or error messages. The DPO is the human overseer who ensures the automated systems are functioning as they should, making informed decisions on which PRS to trust. Furthermore, diligent data recording is a key responsibility. The DPO must maintain a detailed log of which PRS were used, their performance, and any anomalies observed. This log is not just for compliance, it is a vital source of information for troubleshooting issues and for planning future operations. By analyzing past performance data, the DPO and technical staff can identify trends or recurring problems with a specific unit. This proactive approach to monitoring and record-keeping is a cornerstone of safe DP operations, ensuring that the vessel's PRS configuration is always robust, reliable, and compliant with the stringent requirements of the DP2 class. Let's consider a realistic scenario. A DP2 vessel is conducting diving operations 50 meters from a platform, using 2 DGPS units and a fan beam laser system for positioning. Suddenly, a heavy rain squall moves in, obscuring the laser's target on the platform. The fan beam system loses its lock and its data becomes unreliable. The DP system, now relying on only the 2 DGPS units, might sound an alarm. If one of those DGPS units then experiences a temporary signal drop, the DP system could be left with only one valid PRS. This is a critical situation that violates the redundancy principle and could lead to a degradation in positioning performance, endangering the divers below. In this event, the DPO must act swiftly and methodically. The first step is to acknowledge the alarm and immediately assess the situation on the DP console. The DPO would see the fan beam showing an error and 1 DGPS with poor quality data. The immediate priority is to inform all relevant parties, including the bridge team, engine room, and the dive supervisor, of the degraded PRS status. The DPO would then deselect the failing systems from the DP computer's calculations to prevent them from feeding bad data into the position solution. The DPO must then assess if the remaining single PRS is stable enough to safely continue the operation, or if a controlled suspension of work is necessary. The next action depends on the stability of the remaining system and the operational risk. If the last DGPS is stable and the weather is expected to pass quickly, the DPO might decide to hold position while preparing a backup PRS like a taut wire or a hydroacoustic system to be brought online. However, the safest course of action, especially during a diving operation, is often to suspend the work. This would involve safely recovering the divers to the bell or surface, and moving the vessel to a safe distance from the platform until at least 2 independent and reliable PRS are back online. Decisiveness and clear communication are paramount in managing such an event safely. To prevent such scenarios, DPOs should follow strict best practices. Always conduct a thorough risk assessment before the operation, considering potential weather and signal interference. Select a mix of PRS technologies best suited for the conditions. Never start a critical operation without the required number of healthy, independent systems online. Continuously monitor the quality indicators for each PRS, not just whether it is green or red. Finally, regular drills for PRS failure scenarios are essential. This ensures the entire bridge team knows their roles and can execute the response plan calmly and efficiently, turning a potential crisis into a controlled, professional procedure.